Hey everyone, welcome to Tutoring. Hope you're having a great day. Today we are doing chapter 9D, question 17. So we're moving on to a new chapter. I reckon 9A, B, and C are fairly straightforward. But 9D, that's when you start doing your application. That's when things start to become quite confusing. So this chapter is on your difference of rates. So that's when you have something coming inside a tank and you also have something going outside the tank. That's usually the typical questions for this chapter. So this question, question 17, is a fairly standard question, and I just want to make sure that you guys know how to tackle these kind of questions because they are quite common in your SAC, in your exam, and just pretty much in the textbook in general. So if you're really struggling with this, hopefully this video helps you. And aside from that, let's get into the question. Question 17. A tank holds 100 liters of water in which 20 kilograms of sugar was dissolved. Okay, so whenever you're doing these questions, difference of rates, related rates, whatever, any worded question, if you can sketch a diagram, make sure you do. So I'm going to sketch a diagram here. We've got a tank. Don't know what shape the tank is. Doesn't really matter. We'll just get a cylindrical tank in. So right there, that's our diagram. Okay, so it has 100 liters of water to begin with. And then there's 20 kilograms of sugar that's already dissolved. So we'll put your, just put all the information that they gave us, just put it in there in your tank, and then let's keep reading. Water runs into the tank at the rate of 1 liter per minute. So in this case, there is water coming in. We call that dV/dt because it's the rate of inflow of water, so volume in terms of time. That is 1. So plus 1 liter per minute. You can label the units if you want. And then because this is just water, there's no salt, there's no sugar in your water, it's just pure. Your concentration, so we'll call that, usually it's dx, but if you read a little bit ahead, it's m kilograms, so your concentration is actually dm, dv. And of course, it's pure water, so there is no concentration, it's just 0. And that's kilograms per liter. So that's your concentration, mass over volume. Okay. Let's keep reading. The solution is continually stirred, and at the same time, the solution is being pumped out at 1 liter per minute. So that's the outflow. That's what they're telling you. dV/dt, it's being pumped out at 1 liter per minute. You can put negative, but I know it's going to be an outflow, so I'll just put positive for now, and then we just subtract it later. Okay. At time t minutes, yep, there is m kilograms of sugar in the solution, so I've already mentioned that. There's just one key information that we're missing, which is very important in your difference of rates question, and that's your dmdv but outflow. So your dmdv outflow. How would you go about that? Well, I've made a topic video on this, so if you guys want to check that out, I'll leave it on the link below or the pop-up above. Make sure you check that out, and it should really tell you pretty much everything you need to know about difference of rates. So the mdv in this case is actually, like we said, it's mass over volume. So our mass at any time t is just m, right? So m kilograms of sugar in the solution. M is just your mass at any time. And then your volume at any time t is always 100. Because you have 100 to begin with, 1 liter is always coming in per minute, but then 1 liter is also going out per minute. So at the end of the day, the volume in your tank is always 100, regardless of time, right? The general formula, if you want to look at it, is actually the rate of inflow minus the rate of outflow times by t. But because they cancel each other out, you don't really need this the t here. So that's irrelevant, okay? So that's your dmdv outflow. Okay, so you need to make sure when you're doing these questions, you want to sketch this diagram. Majority of the time, your diagram should look the exact same. Something like this. Of course, the numbers would change, but it should look something like this. Okay. Right, and then let's get into answering the question. At what rate is the sugar being removed at time t minutes? So what they're asking here is actually dm/dt, because rate is always in terms of time. Okay, whenever they mention the term rate, the word rate, that's always in terms of time. And because we're talking about sugar, of course, that's dm, not dv. So if you want to find dm/dt, and I'll just put outflow just for you to see, dm/dt outflow is just dv/dt times dm/dv, because then your dv's cancel out and you're just left with that. So dv/dt times by dm/dv. See, your dv's cancel out and you're left with dm/dt. And it makes sense, right? If you multiply volume by concentration, you technically get mass. Just if you guys are doing chemistry. But anyway, this is special. We don't really care too much about that. Let's just multiply. 1 times m over 100, we get m over 100. There we go, okay? So that is your rate of outflow for sugar. That's part A. Let's do part B. Set up a differential equation to represent this situation. Well, of course, our differential equation here is we want to find the MDT again to represent this situation, but this time is net. So we're not just getting outflow, we want net, which is inflow minus outflow. And to do that, it's the same thing, okay? So it's your dm/dt inflow, I'll shortcut that as I, minus your dm/dt outflow. It's as simple as that, okay? And if you want to solve for this, guys, well, we've already found out the MDT, which is outflow, which is m over 100. That's minus m over 100 right there. Now, what's the MDT inflow? Well, is any sugar coming inside your tank? We know that 1 liter per minute is coming in, but there is no sugar at all in your 1 liter. So technically, it's just 0, okay? So your inflow here is just 0. And at the end of the day, your net flow is negative m over 100, okay? So that's pretty much it for part B. Set up a differential equation, which we did. Let's do part C. Solve the differential equation. So yes, this is very common. When they say solve, what they want is they want m as a function of time. So in this case, we know the MDT, I'll write it here so it's clear for you to see, is negative m over 100. Now we just need to solve for m in terms of time. That means just anti-derive. Now we have this right hand side in terms of m, but our left hand side is in terms of t because it's the MDT. So we want to flip it first because we can't really anti-derive yet. Flip it, we get negative 100 over m. And then if you want to solve, we find t, we integrate everything here on the right hand side in terms of m instead. And if you do that, well, yeah, this is just typical chapter 9. So hopefully if you've already done 9A, 9B, 9C, so this one should be pretty standard. Let's solve for time. Time is negative 100 over, of course, anti-diff 1 over m dm. What do we get here? T equals to negative 100, oops, that's negative 100 log e mod of m plus c. Now, depending on your teacher, depending on what the textbook have taught you, there's 2 ways of doing this. One, you can either sub in your m and t values, your initial conditions, so that's 120 into here and then find c, and then of course rearrange it afterwards to solve for m in terms of time. That's technique number 1, method number 1, but what I recommend you guys do is do this instead. So you find m in terms of t first with the c, okay? So you don't sub in any numbers yet. You can find the c later on. So it's because what I've found out is this step is a little bit shorter and quicker and less messy compared to the other step, okay? Especially in like the really more complicated equations. So I'll show you what I mean by this. Let's move the log em over to the other side, and then so that has the 100, and then we move the t over here, so that's c minus t, and then of course log e mod of m. Keep the mod, okay? You can't just take out the mod randomly. Keep it there. Divided by 100, and then mod of m is now exponential to the power of c minus t over 100, or I'll actually write it in this format, so because we're going to do something really cool next, okay? So mod of m equals to exponential to the power of c over 100 minus t over 100. I've just split the fractions apart, and then of course mod of m, here's the cool part, okay? So e to the power of c over 100, you can actually, using minus t over 100, you can actually use the exponential law to split this apart. The exponential law says if you have e to the power of a plus b, you can write it as e to the power of a multiplied by e to the power of b, okay? Or usually it's the other way around, but pretty much that's what this is, okay? So you can actually split them apart right here. So e to the power of c over 100 multiplied by e to the power of negative t over 100. Oh, so over 100 right there, okay? And then now let's get rid of the mod. Of course, mod means it's plus minus m, so I'm just going to divide both sides by plus minus, and you get plus minus e to the power of c over 100 times by e to the power of t, negative t over 100. And then here's the cool part about using this technique. See this part right here? C is a constant, e to the power of a constant over 100 is still a constant, and then you just have plus minus of a constant, right? We're going to have to take out one of the plus minus anyway, so you can actually just go let a equals to plus minus e to the power of c over 100, and then that just solves the headache, okay? Whereas opposed to using this method, the first technique, you actually have to justify where you get the mod. In this case, you just let a equals this, and then when you sum in the numbers, the a solves itself, okay? So m equals to a e, so a is pretty much replacing this, and then e to the power negative t over 100 is still there, okay? So there we go. You have now m in terms of time, m as a subject. The only thing that we have left to do is solve for a, and that's pretty straightforward. We just sub in the point that they give us, and in this case, the coordinates that they give us is mass equals to 20 kilograms at the start, right? So when t equals 0, mass was 20 kilograms. So that's what we do. So sub in t equals to 0, m equals to 20. So right there. And if you do that, you'll get a equals to 20 because e to the power of 0 is 1 and then ma is just 20. So m equals to 20 times e to the power of negative t over 100. And that is your formula for, well, pretty much your differential equation, right? The solution to your differential equation. Okay, so that's part C. And then part D should be pretty straightforward. Sketch the graph of m against t. So the mass against the time. Well, we know from hopefully years of experience in doing VC methods and spec that if you want to sketch an exponential with a negative power, the shape should look like this right here. So that's a reflection upon your y-axis. So it starts from 20 as well, because when t equals 0, obviously, m equals to 20. It starts from here, and we know the shape goes like that. Our asymptote, it's an invisible 0, so really you have an asymptote here. And then all you have to do is just keep sketching it from 20 with that shape right there. Okay, my exponential doesn't look that great, but that's pretty much what you should have, okay? So there we go, guys. That is chapter 9D, question 17. If you, I hope this video made this question a little bit easier for you to solve. And aside from that, guys, thank you for watching, and I'll see you in the next video.